So for this session, we're going to talk about Kepler's laws of planetary motion. This is a portrait of Johannes Kepler. And these laws were one of the first high accuracy models to describe the motions of the planets. Kepler was working off of the observations of Tycho Brahe, who is his mentor. And by using observations of the planets orbiting around the sun and some of the moons of Jupiter orbiting around Jupiter, he was able to develop these three laws that do a lot to describe this planetary motion. Again, this was all done before computers, so these are some of the notes that Kepler was taking, and you can imagine how difficult it would be to actually analyze all of this data of, decades of observations, the observations primarily made by Tycho Brahe. And these are the laws that fit the data that was available at the time. So let's talk about these three laws. We're going to look at some simulations of these orbits in practice. So let's start playing around with this. So Kepler's first law, let's write this down. Is that the orbit of each planet around the sun is an ellipse with the sun at one focus. Already off the bat, there's a lot of terminology here, so we're going to have to be a little bit careful, but let's just write that down. So orbits are elliptical. With the sun at one focus. So an ellipse is a mathematical shape that if I have an ellipse with an eccentricity of 0, then that would be a perfect circle. So it's kind of like, an ellipse is kind of like a circle that's squashed out a little bit. So an ellipse, it's a oval-like shape. So it has a very precise mathematical definition. These ellipses, one of the properties that characterize them is their eccentricity. So eccentricity, it varies from 0 to 1. And this is basically, this eccentricity of your ellipse is basically a measure of how far away from being a perfect circle it is. If it's 0, you've got a perfect circle. So 0 is perfect circle. And 1 is totally flattened circle. So completely flattened circle. The focus, if you have this specific mathematical definition of the focus for an ellipse, there will be 2 foci for each ellipse. They'll be symmetric around this kind of longest axis. And this is just kind of a mathematical property. We're not going to worry about specifically how you calculate where the focus is. But the more spread out it is, the more eccentric the orbit, the further away from the very center of the ellipse that focus will be. So let me just kind of draw this by writing out a couple of examples. So if we have an eccentricity of 0, then our orbit is going to be a perfect circle. This is probably the limit of how close I can get to a perfect circle. And the focus would be right at the middle. So this would be the focus. Technically, there's 2 focuses, foci, but in the case of a perfect circle, they're so close together that they basically overlap. If we have a small eccentricity, so let's say 0.1 or 0.2, then that is going to be a little bit stretched out. It's not quite going to be a circle. And the focus, the 2 foci, are going to be a little bit more spread out along that longest axis. This longest axis is something that we're going to call the major axis, and we'll talk about that in more detail in just a minute. Let me reset my camera. And then if E is larger, so is larger, let's say like 0.9 or something like that, then this shape becomes more and more stretched out, and those two focuses, those two foci, get spread further and further to the side. So for this shape, there's nothing in particular at one of the focuses, but the sun is at the other focus. There's a couple of pieces of information that we want to identify here. So let me draw another example of these ellipses. So let's say this is some particular orbit, and I'm going to zoom in on this one. And let's say the sun is located right here. So here's the sun. There's a bunch of terminology in addition to the eccentricity being how kind of stretched out that circle is. We've got a couple of important points. First, we've got the perihelion position. So let's label this. The perihelion position is the point of closest approach to the sun. So this is the perihelion. So closest to sun. On the exact other side of the orbit, we have what's called the aphelion, which is the point that's furthest away from the sun. So furthest. We've also got what's called the semi-major axis. So if you take that line, that straight line that goes right along the longest kind of width of this shape. Sorry, let me reset my video. If you look at the line that goes along the longest width of this shape, again, this shape, this elliptical shape, it could be tilted in different directions. It could have, all sorts of different orientations. It's a shape that can be embedded in 3D space. But if you look at that longest axis and take half of that distance is going to be your semi-major axis. Which we denote with the letter a lowercase a. We're going to use lowercase a to denote this semi-major axis. So again, Kepler's first law is that the orbit of each planet around the sun is an ellipse with the sun at one focus. So the sun's going to be at one focus. Nothing important that has to be at the other focus. The perihelion point is when you're closest to the sun. The aphelion point is when you're furthest from the sun. The eccentricity is how flattened that shape is, from 0 being a perfect circle to 1 being completely flattened. And this semi-major axis, you can think of that as being the size of the orbit. So you take the full width across the orbit and cut that in half. So again, eccentricity, a measure of how flattened the ellipse is from 0 to 1, with 0 being a perfect circle. There's a couple of equations that we can use to talk about this semi-major axis, which again we denote as a lowercase e, the eccentricity, which we denote as a lowercase e, and the aphelion and perihelion distances. So I'm going to write out just a couple of these equations so we can use them later on. So the aphelion distance is equal to your semi-major axis times 1 plus the eccentricity. Again, this eccentricity goes between 0 and 1. So the more eccentric the orbit is, the further away that aphelion point is. So perihelion distance is the semi-major axis times 1 minus the eccentricity. Couple of things to note about this. If I have an ellipse with an eccentricity of 0, that means it's a perfect circle. So if I have this perfectly circular orbit where the sun's at the center and this planet's going around it, that means the planet's never actually getting any closer to or further from the star. So if the eccentricity were 0, that E value is 0. And then you just have, for both aphelion and perihelion distance, it would just be the semi-major axis. In that case, the semi-major axis would just be what is the radius of the circle. But more generally, if we have an elliptical orbit, one with a little bit of eccentricity, then we can now calculate what is the aphelion and perihelion distance. The last thing to note is, well, let's look at this geometrically. The perihelion distance is, again, the distance from the sun to the closest distance that the planet ever makes to the sun. So it's this distance. The aphelion distance is the furthest the planet makes it from the sun. So this is the aphelion distance, and this is the perihelion distance. If I add that together, if I add those aphelion and perihelion distances, that's just the full width of the orbit, which is the same by definition as twice the semi-major axis. So this last one, you can kind of identify that one using geometry, saying, if I add up the perihelion distance and the aphelion distance, that total distance across the entire orbit will be twice the semi-major axis. So let me write that one down as well. So perihelion distance plus aphelion distance equals twice the semi-major axis. Okay. So let's look at a couple of cases. These are approximately two-scale pictures of the orbits of Mercury and Venus. So if I look at the orbit of Mercury, there's a major axis. This one would be the minor axis, but it's kind of slight, but this is the widest distance across Mercury's orbit. Okay? And the sun would be at one focus of that particular ellipse. We would have the semi-major axis being half of that full longest distance across the orbit. And again, that's, equal on either side. You can pick either side for that. And Mercury's orbit, Mercury is actually one of the most eccentric planets in our solar system. Its eccentricity is about 0.2. So it's about 20% off from being a perfect circle. That's one way that you can kind of think about this eccentricity. Whereas Venus, if we do the same thing for Venus's orbit, this side is a little bit longer. This axis is a little bit longer than this one. So this would be our major axis. Half that distance would be the semi-major axis. And Venus's orbit is its eccentricity is only 0.007, less than 1% off from being a perfect circle. So notice the sun is still at the focus, but that focus is now located much, much closer to the very center of the orbit. It's closer to this case than it was to this case. We can also look at this in terms of where is Mercury at perihelion and where is it at aphelion. So perihelion, if this is the sun, that's the point in Mercury's orbit where the planet Mercury gets closest to the sun. And on the other side of that orbit, that would be the aphelion position, where it is furthest from the sun. We can look at the other planets in the solar system, and these pictures of the solar system, they're a little bit tilted. So we're kind of looking at this with a little bit of a tilt to it. So it might not seem entirely obvious that these are all following ellipses, but for most of the planets have fairly circular orbits. So Jupiter, Saturn, Uranus, Neptune, they're all making a circle around the sun at the very center. But if you look at something like Halley's Comet, it might be a little bit, hopefully it's not too hard to see on the screen. Halley's Comet is a much more eccentric orbit. Hale-Bopp is a ridiculously eccentric orbit. Some of these orbits have different eccentricities. But the overall rule still is that all of these objects that are orbiting around the sun, they all follow ellipses with the sun at one focus. We can actually simulate this. This is the PhET simulation for gravity and orbit. So if you want to play around with this simulation yourself, if you just Google PhET orbits, P-H-E-T and orbits, you can find this program. It's free. You can play around with it all you want. But let's try this. If I move the planet kind of further over here and lower its speed and start playing this, let's add a path. Then as this planet orbits the sun, this is the not to scale version, it's going to draw out one of these ellipses. And again, these ellipses are going to end up having the sun at one focus of this ellipse. So this would be one focus of the ellipse. This would be the other focus of the ellipse. There's nothing much there. But again, we can reset this and have different orbits with different eccentricities. So let me try this one. Some of these might actually hit the sun, so we'll see if this actually hits the sun. So if we let this trace things out, I think we're clear. Notice that it's still tracing out an ellipse. And this axis, if I were to draw this axis, that would be our major axis. So half of that distance would be our semi-major axis. So again, you can use this program, and we're going to look at this a little bit more in just a couple minutes to do a couple more experiments with this. Clear that. Get that out of the way. So again, first law, orbits are elliptical with the sun at one focus, and we've defined some things like the eccentricity of the orbit, the semi-major axis of the orbit, the perihelion position, and the aphelion position. So those are going to be important later on. Okay, let's talk about Kepler's second law. So the second law. The official definition is this: as a planet moves in its orbit, it sweeps out equal areas in equal times. Okay, what do we mean by that? Let's go back to this picture. If I start playing this, and let me clear that, and I'm going to run this for 10 simulated days. So the planet is starting at this location right here. And let's run this. Let's see if I can get 10 simulated days. So kind of do like, go forward one day. Not sure. So 1, 2, 3, 4, 5, 8, 9, 10. Okay. Okay, I did 11 days. So hopefully that's still okay. So during that time, actually, let me go a little bit more. Let's go 20 days. There we go. So now the planet is at this location. And this area here, the area in kind of this blue box, this is what we mean by the area swept out by the planet. If you were to draw a straight line from the sun to that planet and just see how much that line kind of covers up as time goes on, that's what we mean by sweeping out an area. If I then wait a little bit, so let's say we let it go to a different point in the orbit, let's say somewhere over here. Let's try this. So I'm going to stop it here. I'm going to reset that timer, and our planet is starting right here. And I'm going to try to get this as accurate as I can. Another 20 simulated Earth days. So 1, 2, 3, 4, 5, 6, 7, 8. There we go. So now the planet is over here. And we can look at this area, the area that was swept out by that planet. According to Kepler's second law, if you're making these graphs using the same time period, so in this case, we did this kind of 20 simulated Earth days, the area of these two shapes will be equal to each other. Now, in a little bit more of a practical term, one thing that we can look at is this. These shapes, you can think of them as almost triangles. Let me kind of draw this out as a approximate triangle. Again, not super accurate. But if these areas are the same, well, the area of a triangle is 1/2 base times height. So if I want to get the same area, I could have two possible options. I could have a swept out area that has a small base. So this would be the small base, but a very large height. Okay? That would give me a certain area. Or I could have a larger base with a smaller height. Both of those could give me the same overall shape. Well, if we're talking about this in terms of the height and base of this triangle, the height of the triangle, you can kind of look at that as being the height of the triangle depends on how far away you are from the sun. And the base of the triangle has to do with how fast is the planet moving, at least approximately. So this overall leaves us with two general cases. If I'm close to the sun, if the planet is close to the sun, then it's going to have a small height. So in order to have that larger base, the planet's going to have to be moving quickly. If you're close to the sun, the planet's going to have to move quickly. Or if you're far away from the sun and the height of that triangle is very large, then the base is going to have to be small. The planet's going to have to be moving slowly. So rather than depending on this formal, as a planet moves in its orbit, it sweeps out equal areas in equal times, let's try a little bit more practical definition. The planet, during an orbit, the planet moves fastest when it's closest to the sun. So during an orbit, the planet moves fastest when closest to the sun. Again, the official, proper way of describing it a little bit more specifically and qualitatively would be this sweeps out equal areas in equal times. But as kind of a practical way of thinking of Kepler's second law, this second one is probably easier. During an orbit, the planet moves fastest when it's closest to the sun. So again, with this simulation, if I just start playing this again, I'll turn this on fast. When the planet is farther away from the sun, notice it's slowing down as it gets further and further away from the sun. When it's at its furthest point, it's moving the slowest. And then on the other side of the orbit, when it gets close to the sun, it's moving much more rapidly. So near the aphelion position, when you're furthest from the sun, the area that's swept out is narrow but long. Near the perihelion position, the area that's swept out is wide, but it's a shorter area. And that allows these two areas to be equal to each other. And this has a couple of interesting consequences. Again, for an elliptical orbit, when the planet is closer to the sun at perihelion, the planet's going to be moving faster. If I have a planet that's in an orbit with an eccentricity of 0, well, then that planet is following a perfectly circular orbit. It's not getting any closer to or any further from its host star. So in that case, it's going to be going the exact same speed the entire time. On the other hand, if you have a higher eccentricity orbit, there's going to be a greater difference between the planet's closest approach to the sun on one side of the orbit and its furthest distance from the sun on the other side of the orbit. So the greater the eccentricity, the greater the difference between the aphelion and perihelion distances. So you're going to get a greater variation in orbital speeds. Low eccentricity orbits, the speeds basically stay the same because it's just going in a circle. Higher eccentricity orbits, well, you're going to get that close swing by the star, and that's when the planet's going to be moving really quickly. On the other side of the orbit, the planet's going to be moving extra slowly. This is a map of the solar system and looking at the past and future positions of Halley's Comet in the orbit. So notice in 1997 to 1983, Halley's Comet moved this distance, so not very far in about 6 years. From 83 to 85, well, it moved about the same distance as it had in this previous 6-year period, but it made this jump in only 2 years. 2 years after that, Halley's Comet went all the way to the interior part of the solar system and all the way back out in that 2-year gap. Whereas on the outer part of the orbit, from 2006 to where it's predicted to be in 2024, this distance covers an 18-year period, which is probably a smaller distance than was covered in this 2-year period in the inner part of the solar system. Again, this is a demonstration of Kepler's second law of planetary motion. Basically, if you are closer to the sun, if you have a planet with an elliptical orbit, and the points where it is closer to the sun, that's where the object is going to be moving much faster. So that's Kepler's second law. The third law, let's write this one down. There's a couple of properties that we're going to have to talk about for talking about Kepler's third law. Let me reset my camera one more time. We can measure the period of motion, how long it takes an object to orbit its star, and we can measure that in years. So the period, let's get some definitions down. So the period is the time for one orbit. And we're going to measure this in years for the following Kepler's third law point. We can also measure the semi-major axis, and we're going to measure that in AU. Let me just say that we're going to measure this in years. The semi-major axis, we said that's kind of a measure of the size of the orbit. And we're going to measure that in astronomical units. Remember, 1 astronomical unit, by definition, is the radius of Earth's orbit. So essentially, 1 astronomical unit is Earth's semi-major axis by definition. When we look at the motion of the planets in our solar system, the planets that are closest to the sun are moving faster than the planets that are further out in the solar system. These planets that are close in, not only are they moving faster, but their orbit is smaller. They have to travel a smaller distance. So it's going to take much less time for these inner planets to make one full orbit around the sun than the outer planets are going to need. So Mars takes about 1.88 Earth years to orbit the sun. Mercury has a much smaller orbit and takes a much smaller amount of time, about 88 Earth days, to make one full orbit around the sun. So what Kepler's third law does is finds a specific mathematical pattern between the size of a planet's orbit and the orbital period. How long does it take to go through that orbit? So again, more distant planets with a larger semi-major axis orbit the sun at slower average speeds and obey a specific mathematical relationship. And that is the period squared equals the semi-major axis cubed, where again, A is the semi-major axis in AU, and P is the orbital period. Okay? Now, I should mention that this equation is specific for objects that are orbiting around our sun. If you have an object that's orbiting around something else, there are some modifications that you need to make to this. So this is only going to work for planets orbiting around sun-like stars. But let me write down this equation. So the third law is the period squared equals the semi-major axis cubed, where again, this is in years, and this must be in astronomical units. So with this, if I know the size of the orbit in astronomical units, I can use this equation to figure out the period. Or if I know the period of the motion, I can use this equation to figure out what's the size of the orbit, what's the semi-major axis. There's a couple other interesting things about this equation. This equation, again, we're assuming that this equation is looking about for planets going around our sun. So again, if we're going to talk about this in the next session for when we talk about gravity. But if we're assuming we're looking inside of our solar system, notice that this equation does not involve the planet's mass. It doesn't involve the planet's mass, and it doesn't involve the eccentricity of the orbit. So at least according to this equation, the period does not depend on either the planet's mass or the eccentricity of the orbit. I don't care if we have a very circular orbit or a very, very eccentric orbit. If the semi-major axis is the same, according to this equation, the period of motion for that orbit will be exactly the same. So let's play around with a couple of examples on how to use this equation and some of these other equations. I do recommend, as we're starting to introduce a couple of equations, and we're going to be introducing some when we talk about Newtonian gravity and a couple other topics that are going to be coming up over the next few weeks. When we introduce an equation, I do recommend that you start your own formula sheet. Just saying, these are some of the equations that we've introduced. These are, so you have those on hand for when you're doing some of the calculation-based questions. But let's try an example of this. Again, this equation assumes that we are orbiting around the sun. Let's try an example. Let's say we've got the following data, and we want to find out what is the period of Mars's orbit around the sun. We know the semi-major axis, we're given that. We know the eccentricity of the orbit. We know the mass of Mars compared to the Earth. We know the orbital inclination, which is basically how tilted is Mars's orbit compared to Earth's orbit. And we know the rotation period. So let's play around with this. Well, in this case, we're given the semi-major axis, and we're being asked to find what is the period of motion. So let's start just with Kepler's third law. Period squared equals the semi-major axis cubed. Whenever you're using an equation, I do recommend you start by copying one of the equations from your formula sheet without making any substitutions. Well, we said we know the semi-major axis in astronomical units. So this would be 1.524, and that needs to be cubed. So on your calculator, if you plug in 1.524 and you cube that, so multiply it by itself 3 times. I recommend, going through this equation as I'm going through it, but I got 3.54. So 3.54. So now we know that the period squared is 3.54. But we just want the period. So think about this. What do we have to do to both sides of this equation to get just the period? Well, if we have the period squared, and I want to get rid of that squared term, well, I need to take the square root of both sides. So if I take the square root, then this side will just be the period. And if I take the square root of 3.54, I got 1.88. And that would be measured in years. On LonCap, if you use lowercase yr, that will recognize the units as years. So again, just to kind of summarize on the slides, we have period squared is semi-major axis cubed. We know the semi-major axis, so we can kind of identify what that semi-major axis cubed is, take the square root, and we get 1.88 years. Let me try one more version, and I'm going to pause this just to collect some data for this. Okay, so we went through the Mars example where we said, if I'm given the semi-major axis, I can find out the period of motion. But let's see if we can run this equation the opposite direction. So I looked up the orbital period of Saturn, and according to Google, it takes 29.4 Earth years for Saturn to orbit the sun. So that would be the period of motion for Saturn's orbit. Let's see if we can use that data to figure out what is Saturn's semi-major axis. How large is its orbit? So in this case, we're going to have to do things a little bit differently. In this case, we've got the period of the motion, which is 29.4 years. Again, we're still starting with Kepler's third law. So if I take 29.4 and square it, I get 864.4. So 864.4 equals the semi-major axis cubed. But now we have a little bit of this difficulty because we have the semi-major axis cubed, but how do we get that back to just being the semi-major axis? In the last example, when I had something that was squared, and I wanted to undo that square, I took the square root of that quantity. In this case, I've got the semi-major axis cubed, so if I just want to get the semi-major axis, I have to take what's called the cube root of both sides. So at this step, we'd want to take the cube root. So the way that we generally write this out is we make that square root sign and just put a little 3 there. On your calculators, you're going to want to look to see if you have some button on your calculator that looks like this. Okay? Sometimes you'll have something like this, and you'll have to say 3, then this button, and that will give you the cube root, and then you enter in, whatever number you're taking the cube root of. So let's say 864.4 would be the values that you'd input. Or just press, if you have a button that looks like this, you press that button, and then that will let you put the cube root in. Again, different calculators have different setups, so you have to enter the numbers in slightly different ways. But make sure you're comfortable with using that cube root button. If you have questions about how to get your calculator to do that, you can look that up on Google, or you can let me know and come to office hours and we can kind of talk about how to get this calculation working. But back over here, we need to take the cube root of 864.4, and that will basically undo this cube term and just give us back the semi-major axis. So on my calculator, I don't know if you'll be able to see it super well, but I've got a cube root button right there. So it's second function, that one, and it gives me that cube root. And then plug in 864.4. So cube root of 864.4, I get 9.53, let's call that. So when I plug this in, I get 9.53. That would be measured in AU, in astronomical units. And on ln kappa, if you type in capital A, capital U, it will recognize that as being astronomical units. So this is the prediction for we have for the semi-major axis of Saturn's orbit. And if we go to Wikipedia, then and look up that semi-major axis, it's within rounding of what we did for the overall result. So the actual one is 9.58. We got 9.53. Again, the exact time for the orbital period was a little bit low. I did 29.4 instead of 29.4571. So again, it slightly underestimated, but we got something that was in the right ballpark. So as you're working on these kinds of questions, make sure you know on your calculator how to take square roots and cube roots. Make sure you're being careful of what units are being given. If I give you an orbital period in days, before you can use this equation, you'll have to convert those days to years. And there could be some questions where we also mix in things like, oh, if I know the perihelion distance and the aphelion distance, I could figure out what the semi-major axis is. There will be a worksheet based on these sorts of equations, and I will be posting that and making sure everyone knows where to find those materials. So hopefully this gives a little bit of an introduction into how to use Kepler's law. If I know the semi-major axis, I can find the period of the motion, or if I know the period of the motion, I can work backwards and figure out what that semi-major axis is. So that's where we'll end off this discussion on Kepler's laws for now. So again, overall, Kepler's laws, when I have an object orbiting the sun, those orbits are elliptical with the sun at one focus. And we talked about our definitions of eccentricity, the aphelion, perihelion positions, the semi-major axis. For the second law, we said during an orbit, the planet moves fastest when it's closest to the sun. And the third law is this equation, this relationship between the period of motion and the semi-major axis. And also noting that this particular property of the period does not depend on the planet's mass or the eccentricity of the orbit. So that's where we'll call that good for this session.